This is the first of 6 lectures that will make up our 4th theme, where we'll trace the growth of structure, following a sequence from the Big Bang, through sound, to stars, to galaxies, to their web-like distribution. Here's a brief preview of the path we'll take. There are 2 key players in the story, atomic matter and dark matter, and in many ways they act like a team. Each has its vital role to play, and neither, by itself, could create the beautiful universe we find around us. I could almost assign them human roles. Dark matter might be the parent, and atomic matter the child. And without the parent's guidance, the child wouldn't flourish. But what the child ultimately does, the things it makes and the games it plays, are its own creation. Now we, of course, living in our atomic world, are the child, but we should never forget that we wouldn't be here if it weren't for our parent, dark matter, that gently provides a context, a framework for our atomic world to form and grow. So the first lecture in this theme, this lecture, looks at how dark matter makes that framework into which atomic matter will ultimately gather. We start with seed roughness created in the Big Bang and look at how it grows rougher over time. The second lecture walks through the first billion years. Regions of slightly higher density finally halt their expansion, turn around and collapse to form mini halos of future galaxies. Meanwhile, atomic matter falls into these dark matter mini halos and continues collapsing in a runaway process that ends in the birth of the first stars. Then the 3rd, 4th and 5th lectures concentrate on this atomic matter as neighbouring infant galaxies collide and merge to form ever larger systems, ultimately becoming the present-day galaxies that we see all around us. And then in the last lecture, we'll return to look at the large-scale structure of dark matter, the web-like framework revealed by the distribution of thousands of galaxies. This is a dynamic, evolving framework within which atomic matter is trapped and lives out its creative life. So creative, in fact, that of course it makes stars and planets, rocks and trees, and you and me. So this 4th theme has many wonderful things to explore, so let's get started. First, I want to frame the big picture. Remember, the universe is born very smooth indeed, an endless, glowing gas. The microwave background, for example, shows us this gas is uniform to 1 part in 100,000. Now, meanwhile, 14 billion years later, we live in an amazingly lumpy universe. There are vast voids with almost no galaxies in. There are some patches with more galaxies and some regions absolutely crammed with galaxies. It's like a giant 3-dimensional patchwork, mottled, full of denser and less denser regions, going on, filling the universe. So stated simply, the question for this lecture is, how did we get from so smooth to so lumpy? It's a bit like one of those Just So stories by Rudyard Kipling, how the leopard got his spots, or how the camel got his hump, and in this case, it's how the universe got its lumps. Now, there are going to be 3 parts to the story. The first asks, how did roughness start? Can it arise naturally out of perfect smoothness, or must the universe be born with roughness? The next step is to understand how roughness grows. Why do variations in density get larger as time goes by? And lastly, we need to understand why the degree of roughness depends on size. From 1 kilometre to the next, the ocean is very smooth, but from 1 metre to the next, it's very rough. The universe is similar. Why is that? Okay, let's start with the first of these questions. How did roughness start? Now, one possibility is that the universe was born perfectly smooth, and roughness arose out of nothing, naturally perhaps by some kind of instability. Well, in the 1960s and 70s, a lot of thought went into this, and every possible mechanism that was considered wouldn't work. If the universe was born perfectly smooth, it would stay perfectly smooth. And then in the 1980s, as people began to work on the new theory of inflation, it came as a wonderful surprise to find that roughness could be generated quite naturally from tiny quantum mechanical fluctuations that get amplified during the inflationary launch of the expansion. Now, we'll look at exactly how this mechanism works in lecture 32, but the bottom line is that the Big Bang itself makes the initial roughness. So, having postponed answering our first question, let's consider the second one. How does the initial seed roughness grow? So let's start by defining roughness using this graph. Imagine moving through the early universe along a line. The density of matter varies a little bit from place to place. It gets denser and then less dense above and below the mean in a haphazard way like this. The roughness is defined to be the ratio of the variation to the mean. In math terms, the roughness is delta rho over rho, where rho is the average density and delta rho is the small variation. Think of a swimming pool 6 feet deep with 6-inch waves. Its roughness is a 1/12, or about 8%. In this lecture, what we're interested in is how this roughness grows. Now, the average density, of course, drops with expansion, but somehow superimposed on that, the contrast between denser and less dense regions gets more pronounced. Now, as the universe expands, there are, in fact, two rather different ways in which the roughness grows. One is called superhorizon growth, and the other is called subhorizon growth. So I need to explain a little bit about what these rather impressive-sounding terms mean. We've come across the concept of the horizon before, but let's just review it. Out on the ocean, you can see to your horizon. You have knowledge of, you might even say you're affected by, everything within your horizon, but not beyond. And it's like that in the early universe. Every location has a sphere of influence, a cosmic horizon. It's a region across which light or gravity can cross and influence things. Its size is roughly the distance that light can travel since the Big Bang. So 10 years after the Big Bang, your horizon is about 10 light years across. 100 years after the Big Bang, it's about 100 light years across. Now, like the ocean, every point has its own horizon, its own sphere of influence. But unlike the ocean, the cosmic horizons get bigger at light speed. Now, the reason that the horizon is important for the growth of roughness is that roughness occurs across different length scales. Again, a bit like the ocean surface has small waves and long waves. And whether a wave is larger than the horizon or smaller than the horizon affects how it can grow. Here, for example, is the variation in density above and below the average along a line spanning about 1,000 light years. It clearly contains two rather different roughness scales, one short and one long, each shown below. So the top curve is basically the sum of the lower two. So when we speak of a roughness length scale, we're really referring to the wavelength of a particular component that's present in the total. See, in this simple example, we only have two components, and so you can see that their wavelengths are about 120 light years and 8 light years. Notice I use the word wave, as in wavelength, to refer to the up and down quality of the variation, even though it isn't actually oscillating in time, only in space. Now let's compare these two different wavelengths to the horizon. Imagine it's just 30 years after the Big Bang. So the horizon size is about 30 light years, the size of these little circles. So clearly at this time, the large wavelength roughness is larger than the horizon size, while the small wavelength roughness is smaller than the horizon size. Now, this is very important because waves smaller than the horizon and waves larger than the horizon experience two different kinds of growth. Hence, we speak of subhorizon growth for the waves smaller than the horizon and superhorizon growth for waves larger than the horizon. Okay, one last point. The horizon is, of course, getting bigger at light speed, and so before too long, the horizon size catches up and envelops the larger waves. And when it does so, we say these waves enter the horizon. When they do this, they change, of course, from being superhorizon to subhorizon. And so the way in which their roughness grows also changes. So let's now have a look at superhorizon roughness growth. It's actually very simple. Here are three regions. A is slightly higher density, B is average, and C is slightly lower density. Notice that they're all way bigger than the horizon, which has the size of this small circle. So, and this is the important part, these three regions are completely unaware of each other, and they expand just as if they were three different universes with three slightly different densities. Now, here's a sketch of how their size grows with time, their expansion curves. Just as you'd expect, the denser region A is lagging behind because it's held back by the pull of the extra density. As time passes, the difference in region sizes gets bigger, so the difference in region volumes gets bigger, so the difference in region densities gets bigger, so the roughness increases. Basically, the density contrast grows because the denser regions aren't expanding as fast as the less dense regions. Now, this is an exceedingly potent amplification process. For example, during the radiation era, that's before 60,000 years, density variations grow in proportion to time. So from a nanosecond to 1,000 years, the roughness grows by a factor of nearly 10 to the power 20. Now you can see how minuscule seed fluctuations emerging from inflation can end up becoming significant at later times. Okay, now let's look at subhorizon growth. Here's the same situation as before, but with our three regions, A, B, and C, now well within the horizon size. So in this situation, each region feels the gravitational pull of the material within a horizon's distance. So there are local gravitational forces where denser regions actually pull material in from nearby less dense regions, and so they get denser. And then meanwhile, the less dense regions, because they're losing material to the denser regions, get even less dense. So once again, for completely different reasons this time, the roughness increases. Now, this particular process actually has a long history. Isaac Newton thought deeply about how his theory of gravity might apply within an infinite universe. And in a famous dialogue with the theologian Richard Bentley, Newton realized that an infinite static universe would gradually clump up. Places where the density was even a tiny amount more would pull material in from nearby, and so its density would grow, ultimately in a runaway accelerating collapse. In fact, he even wondered whether stars might have formed that way. Now, in our situation, there is one very important difference. Our universe isn't static, it's expanding. Now, this expansion continually dilutes the matter, weakening its gravitational pull. And this seriously affects the ability of roughness to grow by this mechanism. In fact, it's only during the matter era, after 60,000 years, that the expansion is sufficiently gentle to allow some growth in roughness. It turns the runaway collapse for a static universe into a slower growth proportional to the scale factor. So if the universe doubles in size, then the roughness doubles in size. Now remember from lecture 12 that the expansion during the radiation era, before 60,000 years, is more rapid and in a sense more potent. And this basically prevents the growth of sub-horizon roughness. We say the roughness gets frozen at whatever level it was when it entered the horizon. So, sub-horizon growth of dark matter roughness only occurs during the matter era, not during the radiation era. And this will turn out to be extremely important, so hold that thought. Because we have one more piece of prep work to do before we put all this together and understand how the universe got its lumps. So this prep work is to understand how cosmologists describe roughness. Going back to our example from before, it turns out that an extremely useful way to think of any complicated pattern of roughness is as the sum of simpler patterns of different wavelength. In this case, there are really just two of them, short waves and long waves, which combine to make the top curve. But now look at this complex set of density variations, again spanning 1,000 light years. Well, it turns out that this upper curve can be made using the lower curve, which I'm going to call its roughness spectrum, although the technically correct term is its power spectrum. The idea is very similar to a sound spectrum from theme 3. The red line shows the strength of waves of different wavelength that are present in the upper curve. Notice for the x-axis we have long waves, small frequencies, on the left, and short waves, high frequencies, on the right. Remember, these waves don't oscillate in time, they're fixed in space with a wave-like form. So the frequency is really a spatial frequency, meaning the number of waves per 1,000 light years, and it's labelled k, while the strength of each wave is labelled p for power. So this curve is called P of k. Now, you should remember this term from the last couple of lectures on Big Bang acoustics, where I referred to P of k as the pure or true sound spectrum. Now, in that case, variations in the glowing gas were of pressure, whereas in this current context, the variations are in density, and the density of dark matter as well. But either way, you can think of P of k as showing the strength of waves of different wavelength. So the remarkable fact is that you can take a whole set of waves, all with different wavelengths, but with strengths given by this red curve, and you can add them all together, and you can get the top curve. It's really quite amazing. In fact, you can make any graph this way. It doesn't matter what shape it has. You can always find a set of waves that, when added together, make that graph. The person who first figured out how to do all of this, it was in the 19th century. It was a French mathematician called Joseph Fourier. And so these two complementary ways of representing a graph are called Fourier pairs, and the methods used to calculate one from the other are called Fourier transforms. They're really amazing things and are widely used by physicists and engineers. Okay, we're now done with preparation, so we're ready to put all of this together into a single story which tracks the growth of cosmic roughness from the Big Bang to today. So our starting point must be the roughness injected by inflation. Now, in lecture 32, we'll find out that inflation generates a roughness spectrum, what cosmologists call the initial power spectrum, that is particularly simple. It's just P of k proportional to k. So the roughness strength is proportional to the wave frequency. Here's a plot of this kind of roughness spectrum, along with its corresponding density pattern. On very large scales, that's small k, on the left, the waves are very weak. So it's very smooth across gigantic regions. A bit like our ocean. Viewed from an aeroplane, it looks smooth. This is just what we expect. After all, the universe is homogeneous, it's smooth, on the largest scales. And conversely, on small scales, that's large k, the waves are strong. So the newborn universe was much rougher on finer scales. Okay, armed with this initial roughness spectrum, let's now follow its evolution over all of cosmic history. In other words, let's follow how those initial tiny fluctuations grow to become today's web-like pattern of galaxies. Now, the next two diagrams are very important, so try to follow along. Here's a sketch with time along the bottom and size upwards. Both axes are exponential, but we're not going to bother with details of actual numbers, but two times are shown, today and the transition between radiation and matter eras near 60,000 years, which I've labelled equality. On the left are 5 density variations with wavelengths of increasing size 1 through 5. Cosmic expansion makes all of those wavelengths expand, following the yellow lines to the right. They all get stretched in size by the same expansion factor and arrive at their present-day sizes at the top right. Now, the red line shows the increasing horizon size. Remember, it gets bigger at light speed, and where it crosses each yellow line, the horizon envelops that wave, and the wave enters the horizon at the 5 times shown by these little circles. Notice that the 2 shorter waves enter the horizon during the radiation era. The 2 longer waves enter the horizon in the matter era, and the middle wavelength enters the horizon right at the time of equality. Okay, now let's consider the growth of roughness for these 5 waves. In this graph, the y-axis is now roughness, measured by P of k, the strength of those 5 waves, and time is still along the bottom axis. At early times, on the left, the strength of the 5 waves is given by the initial power spectrum, P of k proportional to k, the frequency. So the roughness increases from weak, long waves, that's number 5, to strong, short waves, that's number 1. Starting with the longer waves, 5, 4, and 3, they all grow continuously. They remain outside the horizon throughout the radiation era, and so their growth is never frozen. And when they enter the horizon in the matter era, they continue to experience sub-horizon gravitational growth. But the shorter waves, 2 and 1, enter the horizon during the radiation era, and so their roughness, P of k, gets frozen at that time. They stop getting rougher. Now, as soon as the radiation era ends, their roughness starts growing again, but they can never make up for the lost time, and they end up with less roughness than the longer waves. So, although the initial roughness on the left steadily increases 5, 4, 3, 2, 1, the final roughness first increases 5, 4, 3, reaches a peak at 3, and then decreases again, 3, 2, 1. Let's now see how the roughness spectrum evolves over time. Effectively, we'll move up these green lines, and we're going to ignore the simple cosmic expansion of the wave sizes, so we can concentrate on the roughness spectrum alone. We'll also go beyond the cartoon treatment I've been showing you, and we'll use instead a full calculation using the CMB-FAST computer program from the last lecture. So here's a graph with wave frequency k along the bottom and wave strength P of k upwards, with both axes exponential. You can see how the roughness spectrum increases over time, starting at 100 years, then 1,000 years, then 10,000 years, and so on. So we're jumping by factors of 10 up to today at 10 billion years. So at just 100 years, you see mainly the primordial spectrum, P of k, proportional to k. But as time passes, you can see how the strength of the small waves gets held back when they enter the horizon during the radiation era. But when that era ends, all waves then grow in strength together. So notice that a peak forms close to the size of the horizon, with the primordial spectrum to the left and the suppressed smaller waves to the right. The peak gradually shifts to larger length scales during the radiation era, but settles down to the horizon size at the end of the radiation era, and from then on the roughness spectrum just shifts vertically upwards as roughness grows equally on all scales. So today, after 10 billion years, the universe's roughness spectrum should have a peak whose position is a relic of the transition from radiation to matter dominance around 60,000 years after the Big Bang. Let's see how this roughness spectrum converts to a pattern of density variations along a line. Here's the spectrum with peak and suppressed high frequencies. And in the density plot, you can see how all the very high frequency waves are now gone. And we have quite a chunky graph, with the strongest variations having a scale corresponding to the peak in the spectrum. Now, those density peaks will ultimately turn into huge superclusters of galaxies, while the troughs will turn into enormous voids, and the smaller ups and downs will make individual galaxies. Well, at this point, we really must turn to the real universe to see if all this effort was worth it. In fact, before I do that, I'd just like to acknowledge that this has been a very tough lecture, which probably needs listening to more than once. I deliberately chose to aim high and take you through a topic which is rarely, if ever, presented to non-specialists. So if you've followed even a portion of it first time through, you should feel pleased with yourself. So we're on the home stretch, about to look at the real universe's roughness spectrum, and hopefully it should look familiar. Now, to span the full range of scales, we need two different kinds of data sets. The first are the huge surveys of hundreds of thousands of galaxy positions that reveal the roughness spanning a range of scales from a few million light years to a few 100 million light years. Your eye can already see that the strongest contrast is on fairly large scales, perhaps a few 100 million light years. And sure enough, when you take the Fourier transform, you find a roughness spectrum, P of k, rising for larger scales, shown here as the blue data points. Now, to get data on even larger scales, one must use the patches on the microwave background. Now, these, of course, apply to the young universe, so they need to be adjusted to bring them forward to today's time. But when you do that, you get the red data points, which nicely overlap the galaxy data set, and the overall shape is clear. It has just the form we now understand. From left to right, on the largest scales, the roughness spectrum rises proportional to k. It then passes through a broad peak corresponding to a length scale of about 200 million light years. It then falls somewhat steeper on smaller scales. The black line comes from running one of the best CMB-fast computer models. The fit is amazingly good, right down to the little wiggles on the right. Now, we'll come back to those little wiggles in lecture 22, but let's end this lecture by reflecting on what we have in front of us. We've measured the texture of the universe from 30 million to 6 billion light years. In a sense, this is the inherent large-scale texture of reality, not the particles or atoms of the micro world, but the scaffolding and stage on which the entire play unfolds. Remarkably, there is a scale of maximum texture, about 200 million light years, shown by the peak in the roughness spectrum. It arises because the growth of small-scale roughness was suppressed or held back on sub-horizon scales during the radiation era. If we take the horizon size at that time, about 60,000 light years, and we apply the appropriate cosmic stretch factor of 3700 to bring it up to today's size, we get 200 million light years. The scale of maximum texture, the peak in the roughness spectrum. So the peak tells us the age of regime change, the time when radiation's early dominance gave way to dark matter. That transition, way back in the universe's youth, before even the microwave background was made, is imprinted on the patterns of galaxies across the sky. It's an ancient signature for us to read.